Welcome to our webinar today on additive manufacturing. Just to start off with, for those who are fairly new to Proncia, then Proncia is all about effectively trying to empower our customers through software, services and solutions, really to convert engineering data into actionable information. So our two brands are Encode and Reliasoft. Encode is durability and Reliasoft reliability. And undermining those software brands, we offer many training courses, not just in software usage, but also in the theories behind that. So reliability and durability, fatigue theory, and so on. And obviously we realize that just handing people software isn't usually enough, so we offer several services too. I'm speaking today from materials testing here in the UK, where we obtain material properties just as the ones that we see here are obtained. And we're also involved with providing solutions for our customers, so integrating software within their design, development and test solutions, and also for helping with asset management. If you have a look at our software lineup, you'll notice that there are many different packages under the Reliasoft and Encode brands. Basically, the ones in the left-hand column there, and these are reliability analysis tools, and they're all based on failure data analysis, and that's for helping test planning and system modeling. The tools in the middle column are all about reliability management and how we want to manage risks and maintenance and actions. And the ones I'll be talking about today are in the right-hand column there. These are the Encode tools, and there we're looking at durability, analysis of fatigue and durability based on FE data and based on measured data too. In this particular presentation, then we're concentrating on this one here in design life, and we're looking at design life analysis for additive manufacturing. So this is the agenda that I've got for us today. We're going to start off just by going through an introduction to additive manufacturing, and then I'm going to go through the analysis and the testing that we've done for these particular materials. And anybody who's effectively got our software should find this in the premium data table, the premium materials data. And I'm going to go through here how we manufactured the specimens, how we did the fatigue testing, characterize those, and then look at the results in particular for additive manufacturing compared to wrought materials. And I'm going to finish with conclusion and a discussion on what we're carrying on to do. So first of all then, an introduction to additively manufactured materials. So for many years, Proncia have had a lab here in the UK, and we've done all sorts of testing, fatigue testing on materials. Here you see typical strain life results, that's log of strain amplitude on the y-axis versus log of life on the x-axis. And here we can see typical results for high-strength steel. Don't try and fit a line through those. For this, I've taken a number of high-strength steels, and I've just put them on, so you've got some idea of the range of lives that we get. Of course, we can add to that. So there's an aluminium alloy 2000 series overlaid on top. And if we put a 7000 series, you can start to see how they all fall in a similar band of fatigue lives, a broad band. And if we put titanium on the top, you can see titanium is extending that life quite significantly. And over on the right there, I've given some typical tensile UTS stresses here, 981 megapascals, and 1110. So where does additive manufacturing fit over all of that? And that's really where we were sort of 3 years ago. We wanted to know, just for fun really, if we took additive manufactured coupons, where would they lie in relation to all of these from the historical testing? We chose a titanium alloy, and the UTS was a very credible 1025 megapascal. So in terms of UTS, we were expecting similar results to what we see for the titanium wrought. And those two initial tests based on a selective laser melting came down here. So they were considerably further down, a lot more or a lot less fatigue capable than the wrought materials. And around that time, it was regularly banded by, this is a comment from one of our customers, Additive manufacturing, he said, it's pretty good in tensile, but it's, and I'll leave the dots up to you, but not very good in fatigue. And that was pretty much what we were hearing from all around. You produce additive manufactured materials, they were good, they obtained the tensile stresses that you want, tensile strength, but when you subject them to fatigue, then the lives were orders of magnitude lower than the equivalent wroughts. However, there are many advantages of additive manufacturing, and the industry hasn't stood still. So here's a printout from Aerospace Testing International. This is September 2017, when Airbus completed installation of its first titanium 3D printed bracket on the A350. And that was using additive layer manufacturing in this process. And of course, in the same year earlier, then Norsk Titanium delivered its first FAA-approved 3D printed structural titanium components to Boeing. These were based on a different process. This was a wire-based rapid plasma deposition process. So suddenly, structural items are now being used in aerospace. And therefore, we need to start considering them from fatigue. Additive manufacturing allows an increase in design freedom, and it reduces the need for machining. If you type in a Google search and look at additive manufacturing, you'll find no end of tools, mainly to do with structural topology optimization. And we get these wonderful organic shapes coming out, very light, with all the strength in all the right places. But it's not all about shape. Material strength, and particularly fatigue performance, are crucial. So people are starting to use these in structures. And in fact, if we look at, again, some of the studies, then this one came from a British government study on additive manufacturing. And in 2015, it was found to be worth $5.3 billion, and it was increasing rapidly. In fact, looking at the latest report from the Vola Study Group in 2017, they predict it will rise to £20 billion by 2020. So there's a lot of interest in additive manufacturing. There's a lot of people looking at it too. So as well as the benefits, it has problems that we need to look at. So from the Lloyd's Register report in 2015, they concluded that fatigue is the principal failure mode of structural AM components, and it's a hurdle to its general acceptance. In another report from Lloyd's Register as well, in March 2017, they go on to say additive manufacturing techniques have significant barriers to overcome in developing a manufacturing process that produces consistent quality and safety. And we find that, especially with fatigue, the consistency and quality of those results very much depends not just on the raw material, but the manufacturing process as well. But with these hurdles in place, additive manufacturing still offers significant benefits to engineers. Here's some of the terms that you'll hear. Build from CAD. Additive manufacturing allows for low tooling costs and short lead times. There's no increase in cost. When you've got a small lot size, you don't have to tool up for it, you can print it. In fact, it's ideal really for low volume manufacturing. It accommodates late design changes, and it's good where you've got bespoke customer components or components that are needed to integrate, because they're one-offs and we can print them. It can be used as replacements for forgings and castings. In particular, it has low material wastage, so it avoids us having to machine from a large billet of material. In the aerospace, we call it an improved buy-to-fly ratio. That's basically the ratio between the weight that's flying on the aircraft compared to the weight of the raw material we had to buy to manufacture that component. It also is useful for people in automotive too, because it's now allowing the use of high-performance materials to much lower cost. So already we're seeing people looking at using titaniums in automotive products, because by additive manufacturing, they use much lower amounts of material. So in certain components, we can get that high-performance material at a much lower cost. It's also ideal for manufacturing complex geometries. So there's no cost increase when your part gets more and more complex. And this reduces part counts in assembly. So rather than creating many different parts and joining them together, we can actually start to produce more complex parts in one go. And that improves overall reliability. And obviously, we can use weight saving on those too. It's also ideal for manufacturing legacy parts, so replacement parts, especially in aging aircraft and things like that. And for many years, additive manufacturing techniques have been used for repairing cracked parts, where we can machine out cracks and effectively fill the rest in with additively manufactured parts. And of course, the last one here, but not the least, is looking at supply chain compression for just-in-time manufacture and things like that. So there are many advantages to additive manufacturing, and it's worth, therefore, considering how we can use them for structural components in fatigue. Now, the presentation that I'm giving here was actually given by my colleague, Rob Plaskett, earlier on this year in June. And so everything comes from the ICAF. The ICAF is the International Committee on Aeronautical Fatigue and Structural Integrity. And if you wanted to, you can find a copy of this paper online. It costs about £30 to buy, if in the ICAF 2019 section on structural integrity in the age of additive manufacturing. So I want to go through how we've manufactured test coupons, how we've tested them for fatigue, and what the results show. So let's have a look at the specimens that we're using. So we've used a powder bed fusion process here, and in particular we're looking at two approaches: electron beam melting and selective laser melting. So what we do here is, on that diagram on the right, you can see a rough idea of what it is. We have a powder delivery system, so we start off with the powder metal. That gets pushed up and a roller comes along and it rolls a thin layer of powder over the print bed. We then have a heat source, either a laser or an electron beam in our case, which scans over that and fuses the powders together in the shape that we want. And then we build it up layer by layer. In the end, we blow away all of the residual powder. That gets reused again. And what we're left with is a component. In our particular case, the component is going to be a fatigue sample. Now, there are other processes too. So once we've got that component, we can use hot isostatic pressing or hipping. So we can take something that's been printed using the electron beam or laser selective melting, and we can hip it. So this is effectively where we subject it to a large hydrostatic pressure and temperature. And it has the process of densifying the powder, so filling in all the voids and improving its mechanical performance. In particular here, it's fatigue resistant. And we've also done, as another reference here, we're working with a powder metal company and looking at just hipped components as well. So when we look at this, you'll see that we've not only got additive manufactured electron beam welding and selective laser melting, but we've also got hipped material as well, so we can compare those. In terms of the components, we've used this presentation all about titanium 6Al4V alloy, so titanium 64. We've used, in most cases, cylindrical blanks, similar to the ones that you can see here, with a polished gauge section, 6 millimeters diameter, 10 millimeters long. The only exception here is when we're comparing that with some of the wrought titaniums, where this is in sheet, then we're using wrought sheet, and that's in its annealed condition here. With the electron beam specimens, we've considered 3 build orientations and 2 post-manufacture conditions. So first of all, we've got a vertical build here where it's been built vertically in the chamber layer by layer. And this one is effectively as received. So there's been no post-heat treatment on this at all. There's no hipping. This is just straight from the printer. Now, in the case of titanium Ti-64, in most cases it will be hipped. So we've done another 3 in the hipped condition where we've compared the vertical, the 45-degree, and the horizontal build process to see just how orientation makes a difference to fatigue. We've also got some selective laser melting specimens here. These have all been built in the vertical orientation, but these have been stress relieved. They've not been hipped. And as you'll see, we've only got 2 points at the moment, but we've got a big test program in place to do the rest. And the powder metal ones here, these are actually cut and machined from one large block of material. So a large powder metal block that's been hipped, and then we've cut the specimens from that. In terms of the materials, then if we look at the tensile properties, you'll see that they're all pretty consistent. So there's the electron beam vertical as received. Here's a comparison with the same electron beam with a hip post-treatment. And then you can see the horizontal, see the 45-degree. This one's selected laser melting UTS. And here we could see the powder metal hip. And if we compare those to the wrought material, then with wrought bar, we've got like 981 megapascals there, and a wrought sheet of 1,110 there. So with the UTSs, you see they're all fairly consistent. They compare very well to the wrought bar and sheet that we're using there. So how about the fatigue testing then? So we've used a standard strain life approach for fatigue, like the rig that you see here on the left. If we draw a schematic of that rig, it looks like this. So we've got a test frame around it. We put the specimen in that frame. We mount it in grips. In this case, we've used a wood metal in there so we can get perfect alignment. And we can then pass load through that, a fatigue load through it. We've got a clip gauge that's attached to the side. You can see it in the photograph on the left there. And that's telling us the strain in the gauge section, and that's the control system on this. We're keeping it in a constant amplitude of strain. You'll also see a load cell at the top, so we can see the load going through it. This allows us, if we're in constant strain, when the load starts dropping, it tells us a crack's forming, so we can start to observe the fatigue as it's occurring. You also see there a linear varying displacement transducer there, looking at the displacement of that bottom set of grips. All of these are passed through a digital controller. We can control either in load control, strain control, or displacement control, and everything that you're seeing here is done in strain control. So when we look through those test conditions then, what we see is the tests were done at room temperature in strain control. So the electron beam manufacturing, they've actually all used a triangular waveform because that's what the customer wanted for those. But with the others, we use a sinusoidal waveform at room temperature. All of them were fully reversed, so R is -1. And they all include a soft start as well. So we slowly increase the strain amplitude in the first few cycles rather than going straight for the target cycle, which can prove problematic with the controllers. In terms of the frequency, they all run at a half hertz for the first 43,200 cycles, which is about a day. And then we increase it if or when it's appropriate, depending on the length of the test that we expect. In terms of test monitoring, all test cycles are fully recorded at a high sample rate. We measure the strain in the gauge length, we measure the load from the load cell, and we calculate the stress based on that load divided by the original gauge cross-section area. We stop the test when it's separated, but from the results, we can easily work out the 20% load drop, as you can see here. So the strain here, that top plot, is showing constant amplitude strain, and in the stress just below it, you can see when a crack's forming, we start to get a load drop off, and we typically take the fatigue life as a 20% load drop. You see a few what difference that makes. At separation, we've probably got, in this case, about 19,000 cycles. As we get 20% load drop there, you can see 16,600. So this is our definition of failure. For every test that we do, we produce a little report similar to this one. So it shows us at the top the strain amplitude to make sure the control system was operating correctly. We could see the stress from the load cell load divided by the cross-section area here. And we can start to see, there we go, there's the soft start coming in that I showed you. You couldn't see that in the previous one, but this has only got 900 cycles of separation here, so you can start to see it quite easily. We can see the hysteresis loops. We don't plot all of them. We plot typically one near the beginning, one at the middle, and one towards the end. We can see those cycles to failure due to different failure criterion. As I say, we typically use a 20% load drop here. And here you can see the total stress, total strain, and elastic strain and plastic strain. And it's important to be able to separate elastic and plastic strain. So the plastic strain is actually the distance between these 2 points. So when we look at zero stress, it's the strain between these 2 points. So that's the total plastic strain. The total strain is the total here along these axes. And if we take one from the other, that gives us the elastic strain. And it's that we use, as you'll see later on, in order to characterize the fatigue curve of this material. And finally, you see the waveform here. This one, again, is there in the report, so we can see how well the fatigue rig has managed to reproduce the waveform. You can see there what happens in the load drop. So this green curve here, this is what's happening in a load drop. So you can see it's carrying the full compressive load as the cracks close. But as we start to apply a tensile load and the crack opens, you can start to see now how the apparent stiffness drops off because of the presence of that crack. So we can see very clearly when cracks have occurred. So if we look at those, we also in the lab, we have a microscope. So we look at the failure surfaces and photograph it. If it comes out like this, then this is predominantly plastic failure. We can actually see it's a fairly plastic looking failure. There's no obvious signs of crack growth in there, beach marks and things like that. If we were to compare that with a predominantly elastic one, we can clearly see the crack nucleated here at the surface, and we can see how it propagated and grew semi-elliptically, and then we get the fast failure coming in here. We always observe the surfaces of every specimen we test, and in particular, especially with additive manufacturing, we're looking for this sort of failure. So this is what we call this is a double fisheye failure, and these basic cracks have nucleated from 2 points, and rather than being surface cracks, they've nucleated from somewhere in the middle. And this is usually from porosity or inclusion voids and things like that. And that's very important for us to know with additive manufacturing, how many of these we've got and how they will affect the fatigue performance. Because if there are lots of voids, then the cracks are already going to get an initiation point from them. So it's important for us to know that. How do we characterize the fatigue then? How do we fit the curve? Well, the first thing we need to do is we need to make sure we've got a good account of the plastic and elastic. So this test is showing very clearly high plasticity. So we can tell that by the hysteresis loops that we've got this large amount of plasticity here in comparison to the total strain. We can also tell it and confirm that by looking through the microscope too, and we see this traditionally plastic failure. If we look at that, the opposite, then this one is showing very much elastic conditions here, and that matches with that microscope picture too. The first thing that we fit then is the Ramberg-Osgood, the stress-strain curve. So we fit it in 2 parts. First of all, if we take the stress versus the elastic strain, so we only take the elastic strain now from these 2 specimens. So remember, elastic strain is total strain minus plastic strain gives us elastic. And we're going to plot that elastic strain versus stress. And we fit a straight line through that. When it comes to fitting the plastic part of the Ramberg-Osgood, then we plot the plastic strain here versus the stress. And we plot this on log axes. So we do a linear fit in the log. So these parts down here are all elastic in this case, so they're just quite noisy at this low level. We're looking for that line that fits just through the plastic ones. And once we've done that, we can take those 2 parts, and that enables us to build our Ramberg-Osgood parameters that we need for strain life analysis. We use a similar approach when it comes to fatigue as well, for fitting the Baskin-Coffin-Manson parameters. So here, again, we've taken the elastic strains and we've plotted versus life. So all these grey points are predominantly elastic. The blue are plastic. So in these, we don't consider the plastic points for the elastic curve. We're only considering the elastic points in the elastic curve. We fit this curve through there, and that becomes the elastic part, the basking part of the equation. Similarly, if we were to plot the plastic strain versus life, then again, these are now the blue points, and we're looking to fit a straight line through those blue points. Again, in the plastic region, these elastic points here are just noise, so we're going to exclude those from that. And then once we put those together, then in the same way as the Ramberg-Osgood, we can now start to fit the strain life curve through those points. We do actually do a little bit of optimization at the end of this, just to optimize the sigma f prime and epsilon f prime when you add the two together to make sure that this equation represents the best possible fit. Now, of course, when we want to do this, we don't just want to characterize the regression curve, we also want the design curve too. So this design curve has been fit with a 97.7% reliability and a 95% confidence interval. And again, it's got two different parts to it. So you'll notice that it's much closer in the plastic range because in this range here, the points are actually much more tightly correlated. Whereas in the elastic range, there's a lot more scatter. And that's how we see this design curve in the elastic range having a lot more conservative effect than it does in the plastic. So this has now fitted our fatigue properties, so our Ramberg-Osgood stress strain properties, and the Baskin-Coffin-Manson, which is our strain life curve. We can use that now in the design. So within design life, we use a process called similitude, that if we've done on test, we've got a strain life curve, we've represented stress and strain in that, providing that the strain and stress are the same in the actual component, we can draw in similitude and assume that the fatigue rate's the same too. Of course, if you're using SN, which you can derive from EN curves if you wanted to, all it knows is a similitude based on stress. And then finally, we're going to use a virtual fatigue test here in order to predict those stresses and strains and then predict what the fatigue life is going to be. So what do those fatigue test results look like for Tie 64 then? Well, in order to compare the additive manufactured, what I've got here is I've drawn some baseline values. So these were obtained from our premium database for wrought, bar and sheet. And what we've got here is I've drawn the mean through all of those and I've given plus or minus 3 standard deviations to that in order just to give us a reference. So when we start to plot the additive manufacture on the top, we'll start to see how they really relate compared to the baseline curve. You'll see that it has got a high scatter. I'm not worried about that. It's because we've combined the results from bar and sheet to do it. It consists actually of 2 batches of wrought bar and there's 1 batch of wrought sheet, but it's in 2 different rolling directions, longitudinal and transverse here. Now, if we were to overlay the first one of these, so this is actually overlaying in the blue curve here, we see 15 samples of electron beam melting material with no post-treatment at all. And then the red one is showing 27 samples of the same EBM process, but this time it's being given a HIP post-treatment. So it's showing you the difference. So the first thing to notice, if we look at the blue one, is very low scatter in the results. The life is lower than the baseline, but it's still within 3 sigma, which is good. We notice that the slope, though, is greater than the mean here. And this is probably because with this sort of additive manufacturing, especially with no post-heat treatment, we'll probably find that in the high cycle end, cracks are initiating from inclusions and in porosity and things like that in there. And that's why the slope is steeper and the fatigue is lower, especially at that high cycle end. If we were to compare that, though, with the HIP, then the red line, we see now that there is low scatter in that low cycle region, just the same as before. there's a notable increase, a huge increase in life in the high cycle. So hipping is closing those porosity voids off to make them a lot better. So that's improving massively the fatigue performance in the high cycle range. But it also has a high scatter in that as well, which is reminiscent of sort of quality or probabilistic effects due to that porosity. So this is expected as a result of that HIP post-manufacturing. We've reduced the porosity, and that therefore we reduce the potential for fatigue crack nucleation sites, and that has a huge effect in the high cycle fatigue where the loads are low. But it's had very little difference in the low cycle fatigue where basically the very high amplitude strains are pulling the material apart, so they dominate everything. But as we get to the high cycle where the loads are fairly low, then it's very much dictated by the porosity and the starting cracks. Okay, let's have a look now at what happens with the effect of orientation. So in this case, we've considered the electron beam melting again with HIP, but in the vertical, 45-degree, and horizontal. And you can see here we've got 27 specimens in the red one, that's vertical, and then we've got 15 and 16, respectively, in the 45-degree and horizontal. So all three build orientations show very similar characteristics. We can see that high cycle plateau that we're getting there, and the low cycle, again, it's very similar gradients. Again, there's low scatter in the low cycle region, notable increase in life in the high cycle region, but with a higher scatter in that region. The vertical build generally has longer fatigue lives. So what we could conclude, possibly, that vertical was better, though statistically we can't really draw any conclusion from this because, one, they're very close together, and two, all the vertical specimens were taken from one of the builds, and the 45-degree and horizontal ones were actually built together in a separate build. So the fact they appear to overlay could be because of their fatigue properties and orientation, but it could also be because they came from a different build as well. So it's almost like getting a different material in those. So on this, we can't really draw any statistical significance on whether or not vertical is stronger or better in fatigue than 45-degree or horizontal. But one thing that as engineers we can do is actually we could just take the design curve from the worst condition, and it wouldn't impose too much of a conservatism in using that if we wanted. And then we have benefits in we can use a much simpler FE type approach because effectively we could ignore orientation from all of our models. Now let's just have a look at the effect now of powder metal on this. So those red and blue lines, that's the same ones we've seen. So that's the electron beam melting as a reference. And the first line that we see is this green line here. So this is showing the powder metal hipping. So again, what we can see is a good, consistent sort of quality here. It's shorter life than both the electron beam melting that we've seen in the low region, and fatigue becomes better than the as-built as we get into that high cycle area because of the hipping process. Why do we think it's not come out as good as the EBM? It's probably because when we look at this, we did notice that there's quite a few inclusions in this. And that was probably because when we hipped it, it was hipped into one big billet, and then we cut and machined the components from it. So there's a fair degree of porosity there because of the size of the casting effectively that we made. And probably if we were to reduce that, we'd see an improvement in there. But these are results that we got anyway to share with you. When we look at the SLM, then at the moment I was hoping to share a lot more with you, but at the moment there was only 2 samples of the SLM shown. Much shorter fatigue life here. And for that reason, we decided to delay the SLM testing program, and we're starting that really now. So the SLM program's just started, and right now we're working with TWI, who are doing the builds on this, and they're optimizing their build parameters right now, and they're building the density blocks so that we can look at the porosity and the density of under their manufacturing process. So those 2 points are there at the moment, but we're hoping to see those replaced by a lot more in the next couple of years. So now, just to finish then, by looking at the conclusions and looking at the work that we're carrying on with. So first of all, we've done strain life fatigue damage modeling for electron beam manufactured, additive manufacturing of titanium TI-64. You can start to see here in that top plot, you can see what happens when we look at unhipped versus hipped. And this is a significant benefit. Hipping of TI-64 is very significant in that high cycle fatigue. It's probably wise to only use hipped titanium in this case because of the massive amount of difference that it does. So that HIP treatment improves the high cycle performance, even though the scatter is increased. The fatigue tests on additive manufactured material, we consider this to be essential. You can't infer the fatigue properties based on wrought material. As we saw before, when we compare the wrought material, the additive manufacturing curves are completely different. And it very much depends on the manufacturing approach too. So you really need to do testing and recharacterization, just as we've done here. Treat it as being a different material, if you like, and characterize that material through that printing process that you're going to use. And those curves, therefore, need to consider both that manufacturing process and the material and any post-manufacturing too, because all of that makes a difference. So where have we got to so far? Well, we've done the strain life characterization of the base TI-64 material. That's in bar and rolled sheet in both transverse and longitudinal directions. We've also looked at powder metal hipped. So this is a powder metallurgy hot isostatic pressing. And we've looked at electron beam powder bed fusion. And the electron beam, we've got hipped and not hipped. And we've also got in 3 different orientations too. And all those data are in the premium material database with version 2019 of the software. So if you've got that, you'll find all of those data points in there for doing fatigue of the additive manufacturing TI-64. We're now going on and we're doing a lot more on that selective laser melting. So remember, we started with just 2 points, and that was enough to realize that we needed help in the manufacturing of this. So this year we've started a 3-year research project that we're doing together with TWI. So TWI, the Welding Institute, are working with us on this 3-year project, and this is considering SLM, not just of titanium, but we're extending this to aluminium and to nickel alloys as well. We're going to be looking at lots of different approaches in this too, like looking at mean stress effects, surface effects, and looking at how different print things affect fatigue too. We've also got a project running with Cranfield and Coventry University. So this is we're helping to support their 5-year project in WAM. So this is wire arc additive manufacturing. And this is also going to consider titanium, aluminium, and steel alloys as well in this case. And in addition to that, we're also working with TWI to look at small component tests too. So having obtained the material properties, we want to see when we actually manufacture and print real components, how accurately are we able to predict the fatigue life? In theory, we should be able to predict them as goodly as well as the specimens for fatigue. But we want to be able to do that, and we want to look at what the problems are. In particular, look at things like support structures and their effect and things like that when we're looking at component validation. So if what I've talked about today has been of interest to you, then for the ICAF seminar, then a paper for that was published, and you can download that if you want to. So that's if you go to the ICAF 2019 Structural Integrity in the Age of Additive Manufacturing, if you look down that page, we're the 4th one in the list, It costs about £30 to buy that paper, and that covers the slides and everything that we've seen here.